Hey, all. Had a question on this one, and I totally get where the student asked this. He said, wouldn't if the derivative and the integral are inverse functions, wouldn't the result of the derivative of the integral end up just being the function f of t in this problem? That's not the case. Let's go ahead and show why. So we're taking the derivative with respect to x of the integral from a to x of f of t dt. Okay, now, whenever we integrate uh, to show an antiderivative in just general terms, if we don't have a specific function, all you have to do is capitalize it. So the antiderivative of lowercase f of t is capital F of t. Okay, so when I try to do the inside here, here's what happens. I'm still taking the derivative with respect to x. The integral of f of t dt is capital F of t, but now I'm evaluating that at the definite integral points a and x. Now think about what happens with that. You're still taking the derivative with respect to x. When I evaluate the inside at x, it's the antiderivative, not in terms of t, but in terms of x, minus the antiderivative evaluated at some constant a. Now, when we take our derivative, we know we can take the derivative of the first term and then the second term. Derivative of the first term is just going to be the derivative of the antiderivative f evaluated at x. And then we know that the derivative of any constant is just zeroed. So the derivative with respect to x of the function evaluated at any constant is just going to give me a zero. Now, by definition, capital F prime, it's equal to just lowercase f. So we would say, well, this is nothing more than the original function in terms of x. But that's why, yes, the derivative and the integral are inverse operations. They undo one another. But in this case, it's going to be the function evaluated at x because of what your limits of integration are. So if we were to simplify this out here, we need to put an f of x there. So if I tried that and say f of x, check that, and it's saying excellent. Why, thank you. Now, in the next one here, ooh, I like this. Think about this one. It's having us take the derivative with respect to x. Now we're just integrating on the integral a to b, where a and b are understood to just be constants of f of t dt. The key in this one is for you to understand that, well, we're going to be taking the derivative with respect to x of this group, and the group is just going to be the antiderivative evaluated at the constant b minus the antiderivative evaluated at the constant a. No matter what, the inside, both terms are just constants, and we know that the derivative of any constant is zero. So anytime you don't have variables for your limits of integration that are not in terms of what you're trying to take the derivative with respect to, your answer is always going to be zero. So for this one, we would go in and say that one's a zero. And good job. Thank you. And I believe that's it for that problem. Okay. Now, one other thing I would like to mention here, and it's not in this problem, but it will be in some other ones, is hypothetically, what if I would say I want you to take the derivative with respect to x of, let's put variables for both limits of integration. Let's say uh, my upper limit is the sine of x. My lower limit, I'll let be x cubed. And then my function on the inside, I'll leave it just the same as this, f of t dt. So now I'll be taking the derivative with respect to x of the antiderivative of f of t, which is going to be capital F of t. but it's going to be evaluated at these limits of integration, both in terms of x. I'll have from x cubed to the sine of x. So I'll be saying this is the derivative with respect to x of the antiderivative evaluated at the sine of x minus the antiderivative evaluated at x cubed. Now, due to the chain rule, it's not going to be as simple as it was up here. I can't just say, oh, well, the derivative of the function, that's going to take me back to the lowercase f evaluated at the sine of x. That's true, but there's more to it because the integral had no way to account for the fact that you're putting a function inside of a function. You weren't when you were just integrating, but then when you evaluated, you're putting a function inside of a function so that when you take the derivative, you're going to have to say, well, it's the original function evaluated at the limits of integration times the derivative of the limit of integration due to the chain rule. So for this one, I would say times the derivative of sine, which is going to be times cosine, and then minus our lower limit, which would be the original function evaluated at x cubed, times the derivative of what we plugged in, 3x squared. That would be my final answer there. Gorgeous problem. But do keep in mind this little addition I made to this problem because the problem as is was okay. It's beautiful once you start thinking about this addition. All right, guys, let me know if you have any questions.